All right, good morning, everyone. Thank you, and good morning. My name is Ron Ashburn. I'm Executive Director of the Association for Iron and Steel Technology, and it's my honor to welcome you all to Detroit, to AISTech, and to this very special 100th anniversary of our Howe Memorial Lecture, which does represent the opening session for our conference this year, and arguably perhaps one of the longest running lectureships in the entire global steel industry. Before we begin, I would like to point out our emergency egress points in case we need to evacuate. You'll exit the doors in the back. You're going to turn right, proceed down the steps to level 2, that's the street level, and exit out onto the street. And although this is our opening session, we actually kicked things off yesterday with the AIST Foundation Golf Classic. I want to thank all of the golfers who came out and weathered the little bit of rain. The event was sold out and raised almost $30,000 for the AIST Foundation Scholarship and Grant Program. So another great day yesterday. Starting this morning, this year's technology conference will include 445 presentations representing over 1,100 authors from 33 countries. So it is indeed a global technology conference for the industry. I'm pleased to report that we have almost 7,000 people registered for AISTech this year, which makes it one of the largest events outside of Pittsburgh in our history as well. So thank all of you for showing up to make that happen. Tomorrow morning at 8 a.m. will be the President's, the President's Award Breakfast. It'll be featuring John Brett. John's Executive Vice President and CEO for ArcelorMittal North America. That event is filled to capacity, but it will be streamed live as well. And then Wednesday morning, starting at 10 a.m., will be the Town Hall event, and we'll have 5 industry executives this year, including Tracy Forrester from Cleveland Cliffs, Rich Fruhoff from U.S. Steel, we have Barry Schneider from Steel Dynamics, Sushma Walker from Nucor, and Mike Williams from Timken Steel. So an all-star lineup there. It is a can't-miss event, and I do encourage you to get there early and get a good seat, hopefully up front. We will stream that event live as well. And running today through Wednesday will be the exposition, our largest ever in all respects, really. It has 588 companies. We will have a reception this evening, Monday night, and Tuesday night from 4:30 to 6 in the exhibit hall. And we'll give away that bright red Chevy Silverado pickup. If you haven't seen it, it's in the back left corner of the exhibit hall. We'll give that away to some lucky recipient on Wednesday at 2:30 in the afternoon. But you do have to be present to win. So I do want to thank all of our exhibitor companies, 588, that's a long list of companies, and we appreciate their efforts to be here and be part of AISTech. Now, before we begin, I do want to point out, you need to have one of these blue badges to be, or an orange student badge, if you're a student, to attend any of the technical presentations this week. If you don't have the appropriate badge, please go down to the level below to the registration area, and you can obtain one there. I would ask that you mute all cell phones while you're in any session this week, and remember that the recording of our presentations at AISTech is prohibited. Now, the Howe Memorial Lecture was established in 1923 to honor Henry Marion Howe, and as history tells us, Dr. Howe helped turn steelmaking from an art into a science with his gift of observation and deduction. He studied the breakthroughs of others and added to them with his own investigations and insights to establish the field of metallography. And over the last century, the Howe Lecture has welcomed 89 of the best and brightest minds to the conference stage to share their insights on steel. The extraordinary work of all Howe lecturers, past and present, has shaped our modern understanding of steelmaking as a science, and their work will undoubtedly inspire more innovation in the future. In celebration of the 100th anniversary of the Howe Memorial Lecture, I would like to take a moment and recognize some of the past lecturers who are here with us today. We go back 34 years. So from 2015, our lecturer, Yakov Gordon, and I'm going to ask you to stand, Yakov. From 2009, Brian Thomas. And from Rod Guthrie is registered from 2000, but I don't see Rod. Oh, Rod from 2000. And going back to 1989, Toshi Emi. So please give these gentlemen a warm welcome today. Our past lecturers are pioneers in their own right, and we're grateful that they could be with us here this morning. So thank you all, gentlemen. Now it's my distinct pleasure to introduce the 100th anniversary Howe Memorial Lecture. Information on the legacy of the lecture has been looping on the screen. I hope you had a chance to check that out, including the biography of this year's recipient, Dr. Ron O'Malley. Ron is the F. Kenneth Iverson Chair of Steelmaking Technologies, and he's the director of the Kent D. Peaslee Steel Manufacturing Research Center at the Missouri University of Science and Technology. Time permitting, he will answer Q&A sessions. He will have a Q&A session at the conclusion of the lecture, and we will formally recognize Dr. O'Malley tomorrow morning at the President's Award Breakfast in the ballroom. His lecture this morning is entitled Fiber Optic Sensing Technologies, Supporting Advancements in Steel Production and the Shift to Industry 4.0. He is a compassionate leader for AIST. He's a true champion for steel. Please welcome Dr. Ron O'Malley.
Thank you. We'll do a microphone test. Can you hear me? Perfect. Excellent. Well, what an honor to be here today in front of my colleagues, many of whom I've worked with over many years, and it's a real joy to be here and to talk to you today about a topic that I'm very excited about, and that's the fiber optics technology applied to steelmaking technologies. So Ron already highlighted some of the attributes of Henry Marion Howe, and I wanted to just emphasize those. One of the things that Henry Marion Howe did was actually take the art of metallurgy and transition it to a science. And he was very successful at doing that, publisher of one of the early metallographic texts in the industry. And overall, his impact over the years led to a large number of individuals who have continued that contribution. And Ron already showed a list, but I wanted to just put that list up here again. You know, as I look through this list, there are so many people that I know from my time in the industry, so many people that I have great respect for that have helped me in my career. And I just wanted to say thank you to all of them for laying the groundwork for the future of the steelmaking technology area. I did want to highlight one area that is particularly, I'm particularly proud of, and that is, as I look back at some of the past selections for the Howe Lecture, my advisor, John Elliott at MIT, was a previous speaker. And not only that, but his advisor before him was also a Howe Memorial Lecturer, and that's John Chipman. And as I go back and look further, Henry Marion Howe himself also was a graduate of MIT. And so there's a long legacy for MIT's involvement in steelmaking. And I'm really proud to be here today to carry on that legacy. So we're going to talk about fiber optics, but I want to basically first talk a little bit about Industry 4.0. And you all know that Industry 4.0 refers to the fourth industrial revolution, which affects every manufacturing domain, not only steel, and advanced manufacturing technologies that capture, optimize, and deploy data. Boston Consulting Group identified 9 key areas that drive Industry 4.0 methodology: additive manufacturing, augmented reality, autonomous robots, big data analysis, cloud, cybersecurity, horizontal and vertical systems integration, Internet of Things, and simulation. All are components of this Industry 4.0 thrust. One of the things that is important for all of these areas is for the steel industry, really all of these technologies rely on the sensing and measurement technologies to actually enable Industry 4.0. And in particular, I'm really interested in it from the standpoint that we deal in an extreme environment. You know, the temperatures and the conditions within the steelmaking environment are tough environments to measure temperature, strain, position, composition, and so forth. However, the Industry 4.0 methodologies really require these inputs to support things like artificial intelligence, big data analytics, neural nets, Internet of Things, augmented reality, robotics, and digital twins. In order for these things to work, we need to be able to measure and verify these systems, and it's key to continue the push to develop new sensor technologies. And from my standpoint, one of the big interesting areas in steel measurements is the application of emerging fiber optic sensor technologies. And steel manufacturing, is a key area where we can apply some of these new technologies. So what are fiber optics? Fiber optics, simply put, are light pipes. They actually transmit, light energy through the core of a fiber with low attenuation so that you can actually send this signal from one location to another. Those systems also can be configured in such a way that they can measure things like temperature, strain, and even chemistry. And those measurements are actually really important to our industry. And fiber optics actually provides a really interesting methodology to do these measurements in the hostile steelmaking environment. So if you look at it, some of the advantages of these fiber optic systems are that they're small and lightweight, they're immune to electromagnetic interference, they're resistant to chemicals, chemical corrosion. They have, it turns out, in many cases, high temperature capabilities, very high sensitivity. They provide the ability to do remote sensing with interrogation units away from the high temperature environment. And then finally, they actually provide a unique opportunity to do distributed sensing capability where many measurements can be made along one fiber. Fiber optic sensors come in a whole variety of forms, and I just want to highlight some of these fiber types and some of the sensing methods that are used in them. Fiber types typically consist of either a single mode or multi-mode fiber. In a single mode fiber, the core of the fiber is actually small enough in diameter that there's only one light path that the light can travel. And as a result, we can use time of flight to actually monitor position along the length of the fiber. Many fibers that are used in telecommunications actually utilize this approach. The core of the fiber actually has a slightly different index of refraction than the surrounding casing for a single mode fiber. And it's that slightly lower external index of refraction that is usually generated by doping the external clad that actually provide this ability to contain the light. There are also different types of fibers from the standpoint of core diameter in single mode fibers, and that is that you can have different diameters that lead to different what are called numerical apertures for these fibers. And what that does is it actually turns out to be an important tool to allow you to tune the properties of these fibers so that you can do things like separate temperature and strain measurements. So sensing methods that are used with fibers, optical signal transmission. Here we can use a pyrometer type signal or a spectrometer type signal, transmit it through a fiber to a remote device and collect information about it. Interferometry, it turns out that if you reflect light off of the end of the fiber and off of a target external to that fiber, we can actually generate an interference pattern that can be used for measurement. Fiber Bragg gratings is probably the one that most people in the industry here know, because FBGs or fiber Bragg grating systems create a reflection that is fundamentally tied to the spacing of the Bragg gratings themselves. And that frequency can shift as a function of temperature and strain, and therefore produce a measurement. And each Bragg grating can be individually identified to identify a base frequency and the frequency shift for that measurement. And the one I'm really most interested about and would like to talk more about and show you today is a technology called optical frequency domain reflectrometry. This technology actually is relying on the natural inhomogeneities in a fiber. And various types of scattering occurs, back reflections occur in that fiber due to the natural density fluctuations in the fiber core. The advantage of that methodology combined with a single mode fiber is that it allows measurements to be made, in some cases, at very high resolutions, on the order of 0.5 millimeter spacings along a fiber that can be hundreds of meters long. And as a result, you can use one fiber off the shelf without having to impart Bragg gratings to actually get highly distributed temperature or strain measurement. And we'll talk more about that in a bit. So there are various types of scatterings that can be measured in the optical frequency domain, and that is Rayleigh scattering, which has the highest resolution, Birolian scattering, which has a lower resolution but much longer transmission length, and Raman, which is almost equivalent to Birolian in terms of its extended lengths. So I'm going to be talking more about all of these. And just to start off with, one of the simplest form of sensors that can be manufactured with a fiber is an interferometer. And an interferometer basically looks at reflected light off of the end of the fiber and reflected light off of a target, collects those reflections, and actually monitors the behavior or the distance between the target and the end of the fiber based on its interferometry signal. So those two signals create an interference pattern. That interference pattern is directly related to the gap between the end of the fiber and the target, the index of refraction of the medium in that region. And it turns out for things like temperature measurement or space measurement, these types of sensors can be used for very accurate position measurements. In many cases, under conditions where they're exceptionally insensitive to temperature. And I'll show you some examples of that later. So the other approach here with these types of sensor systems is that they're single point. They can be used either as an intrinsic fiber where the sensor is built in at the end, or you can have a reflection off of an external target. And the plot to the right basically shows how that spectral shift occurs as a function of temperature for a sensor that has an intrinsic interferometer. I'll show you some other examples where we can use these types of systems to actually measure the evolution of gap during solidification shrinkage, or even interrogate flux layers in the continuous casting process. The most common method you'll see out there, and many of you have seen these in continuous casting molds, is the fiber optic sensing system using Bragg gratings. Bragg gratings are generated with a fixed spacing between those etched Bragg patterns such that the reflected frequency is a function of the spacing of those Bragg gratings. And so each grating is etched into a fiber as a sensor. It can be etched with a certain spacing that gives you a base frequency. But frequency shifts as a direct result of temperature or strain due to something called the thermo-optic coefficient or the thermal strain coefficient. And as a result, this type of technology is very well suited for measuring temperature shifts and strain, in some cases to very high temperatures. And I'll show you some examples where these types of fibers of the right type can actually measure temperatures up to 1800 centigrade. This is the Rayleigh scattering, and this optical frequency domain reflectrometry actually is based on these inhomogeneities within the core of the fiber. And as a result, if we interrogate that fiber and collect the Rayleigh scattering signal in a back reflection, we can get a particular spectrum that is distinctly associated with each section of the fiber. When the conditions at that location on the fiber change, that pattern remains but shifts in its frequency. And so we can use cross-correlation methods to actually interrogate about a 0.5 millimeter space along the length of the fiber. And that leads to what is essentially a near continuous temperature measurement. And this just shows some of the interrogation systems that are used to collect that and some of the fundamentals behind it. So if I show you some of these measurement systems, you'll notice here that we actually have a system that can be calibrated both to temperature and to strain. And one of the challenges in these types of fibers is actually distinguishing what you're actually measuring, temperature or strain. And it turns out there are some really interesting ways to do that. You can either isolate the fiber from strain and measure temperature, or fully connect the fiber and measure a combination of temperature and strain. But we can also use different fiber numerical apertures in the same configuration and deconvolute the temperature and strain signals directly by actually comparing signals of two different fibers with different numerical apertures. And so a 2-fiber run can actually do a deconvoluted temperature and strain measurement, which is pretty exciting. So you'll notice here, if you look at the bottom right, you'll notice that there's a plot going up and down in temperature, superimposed on it a thermocouple, right? And you can get an idea of how accurately these things trace and predict the temperatures based on their frequency shift. But that comparison is a little deceiving, because what you also get is the information on the bottom left, which is the full temperature distribution along the length of the fiber. So running one fiber through your furnace or in an environment will actually give you the whole profile. And that's really exciting stuff. So there are a number of different methods that I've already highlighted. And I just wanted to summarize some of them here, because each has its own distinct advantages and disadvantages. If I look at fiber Bragg gratings, typically the maximum spatial resolution you can get out of those fiber systems with Bragg gratings etched on them is about 5 millimeters, which is great for a lot of applications and actually being used in continuous casting molds today. They can sense, though, at very long distances, up to 10 kilometers in length. But their one restriction is that typically you're limited to the number of sensors you can put on the fiber, because each one has to have a distinct frequency. And so typically we can have maybe up to 128. Many systems that I see out there are limited to 50 or 60 sensors on a fiber. But with that, you can go over very long distances and do point temperature measurements. So it's kind of a quasi-distributed measurement system. Temperature or strain can also be measured. The other thing about Bragg gratings is that they can be used not only in single mode, but they can also be used in multi-mode fibers, where the core is so thick that you have multiple light paths, and you can no longer use time of flight for position measurement. The frequency defines the position based on the frequency you set along the fiber. And these fibers can actually reach temperatures up to 1800 C if you use certain fiber types, like single crystal sapphire fibers, which can now be grown in up to 2-meter lengths. So I'll show you some examples of that as well. So these multi-mode fibers typically are undoped. Oftentimes they're not cladded. The air around the environment is the cladding that contains the light, and that works for a lot of systems. In these systems, we can use undoped fibers, which can reach temperatures above 1000 C in applications. Whereas if we go to Rayleigh scattering, for example, we use a single mode fiber only. It can measure 0.5 millimeter resolution, and its temperature limitations are a little bit lower because of the dopant migration, about 700 C. So there's also other measurement methods, Brillouin scattering, which is just, it's a method like Rayleigh scattering, except the scattering is in a different frequency domain and essentially initiated by different origins in the reflection spectrum. But those typically have a much lower resolution, on the order of 0.5 meter, but they can continuously measure over, again, tens of kilometers of length. So this just shows some of the comparisons of the ability to the number of channels and the cost of the systems and so forth, and you get some feel for what the temperature capabilities of each of these are. So I want to now just talk a little bit about how we use some of these fibers. And today, some of these fiber systems are already being introduced into the industry for a lot of uses. And just to give you a few examples, here's a system that is the Chameleon system by Heraeus electronite. And it is actually a consumable fiber that is injected into the steelmaking environment, the EAF or LMF environment. The fiber is consumable, it's protected and jacketed, and it actually measures the thermal emission and carries it back through the fiber to measure, essentially through an optical pyrometry method, the temperature at the tip of the fiber being introduced and ultimately consumed. The beauty of this method is that that tip of that fiber actually acts as a black body radiator, and so emissivity corrections aren't required, and so you can get a very accurate temperature measurement. There are some other advantages of this system is because the fiber is being introduced and consumed, we can also do things like track interfaces, such as slag and metal bath heights in these systems. And we're working actually with Heraeus on some other ideas to incorporate composition measurement in these kinds of systems as well. There are a number of people that are marketing sensor systems to go into the refractory linings of your steelmaking vessels. And there's a couple of them that are out there that have largely settled on the use of either beryllium or Raman backscattering, which, as you remember, is relatively low resolution. It's about a half a meter measurement length accuracy. But when put into a lining of a vessel, these things can actually still give you a lot of very good detailed information related to hot spots in the sidewalls of refractory systems. And we'll talk more about that later, but this just shows a couple of systems that are commercially available today to do these types of measurements. One of the biggest areas we're seeing an influx of fiber optics is in the continuous casting process for measurements of mold thermal behavior. And the standard right now for these technologies are based generally on fiber optic sensing methods using Bragg gratings. These Bragg grating methods, as I mentioned, can measure resolutions down to about 5 millimeters and can map the thermal behavior in a mold over a wide area. Here, each trace is actually has a number of sensors on it, and each trace is an individual fiber feeding one line in this case. That information is taken back and converted into a thermal map, and these things are used not only for sticker detection and continuous casting, but also thermal monitoring to essentially evaluate mold thermal behavior, flux behavior. This particular system is an SMS system, which is implemented in a lot of plants today in the US, and people are really now beginning to use them to learn more about their processes, because these are tools that can help you understand and develop mold flux performance and other things that we'll show actually in a bit. You can see also that these things can map and trend and also ultimately be used to assess quality of the product. And one of the big fertile areas for Industry 4.0 is tying these types of outputs to quality systems to actually do directly linked measurement and prediction of quality events in the casting process. There are others out there, and this happens to be one of the more higher resolution ones that I've seen. In this case, each area shaded actually is an individual fiber, and each fiber has between 21 and 26 sensors etched on it. Here they've actually mapped a much higher density around the mold meniscus area. And the advantage of doing that is we can now thermally trace the meniscus and the meniscus shape. And here are some examples of that. Here we can actually see standing waves, flow asymmetries, sticker events for sticker detection, but you can actually track and monitor that wave shape. And it can be tracked in real time. And so, one of the things we always worry about in the casting process is to make quality steel, we have to minimize the wave asymmetry and turbulence in the mold. And so here, this is a really valuable tool to actually tell what your mold profile is looking at. Before this, the way we used to measure these systems is we would put nail boards or shims in the mold and do a spot test, right? But now with these systems, it's becoming increasingly more valuable to actually see these things dynamically. So here's actually an example of some dynamics in the casting process. You can see how that meniscus behavior is fluctuating. You can actually see the thermal profile lower in the mold down below as well. And there's some things about the lower region of the mold we'll talk about in a minute. But all in all, these are great tools for studying the stability of flow in certain submerged entry nozzle designs, the efficient use of electromagnetic braking, and also the development of mold fluxes. So here's just another trace showing one of the common things that is seen in thinner slab, very higher speed casting processes is the onset of flow asymmetries. And these can be offset just by flow instability from a submerged entry nozzle. These asymmetries can occur on a regular pattern over a long period of time, sometimes switching on the order of 5 to 15 minutes. They also can be initiated by clogging events that lead to asymmetries in flow. And this just shows a commercial system that's available that is now able to track these things. So this is actually a slide that Brian Thomas actually put together, and it shows how these fiber optic mapping systems can be modified and interrogated to identify high-risk regions for longitudinal cracking, for example. You know, and up to this point, conventional breakout systems did not have the resolution to do this type of measurement and sensing well. But in these new high-density fiber optic systems, they're very good at detecting these asymmetries and anomalies. And given that these longitudinal cracks can have very narrow spatial width, you know, it requires high-density measurements in order to identify them. So in my past, we've used traditional thermocouples to monitor the stability of the continuous casting process. And in that work, we've actually identified some key mechanisms that create instabilities. And this is an example of a thin slab mold where the funnel area, actually, let's see if I can get that pointer to show. I guess it's not. Anyway, in the lower right, you'll actually notice that there is some fluctuations in temperature that show a sawtooth type pattern low in the mold that is existent only in the root area of the funnel. Outside of that area, the temperatures are very stable. What causes that instability, it turns out, is the stability of the mold flux crystalline layer. And in the upper right, I actually show in that light orange layer in that flux film what that crystalline layer looks like when it's stable. But in the lower right, you can see where when that flux film is extracted from the root area of the funnel, that film has fractured. And in fact, what we see in these sawtooth fluctuations is the extraction of that crystalline layer, the formation of an air gap, infiltration of that air gap with glass. That brings the heat removal up high, and then you can watch the slow crystallization of that layer to lower the heat removal. And this occurs repeatedly over time. Well, with these types of systems, we were still very lucky to catch this, because even in this densely instrumented mold, we were lucky to catch that type of behavior in the funnel root area. And by the way, with conventional sensors, breakout detection systems, or mold heat removal measurements, you would never see this behavior. It is hidden by the fact that it's in a small area relative to the total heat removal of the process. But it is very disruptive, and it's one of the reasons that sometimes these types of mold designs actually exhibit centerline longitudinal defects. And the key to solving that problem is developing these flux films so that they remain stable under the stresses of the withdrawal environment of the casting process. With these new fiber optic systems, we can see these behaviors directly. And you can see here on the left versus the right, different fluxes in different steel environments that show essentially jumping behavior as a function of time lower in the mold that is directly related to this film sheeting behavior. If that sheeting behavior travels too far up close to the meniscus, we have catastrophic events take place. And I think I've also, this is actually a video just showing the dynamics of a lower part of a mold that exhibits this periodic sheeting behavior. You can see it's not always uniform. This happens to be sheeting in the lower part of the mold, but we can actually watch that instability. And a lot of this has to do with how the flux is designed, how thick and rigid the flux film is, and its ability to resist shear in essentially the stresses associated with the casting process. Of course, the holy grail is to actually use a system like this and close the loop. And here is a proposal for a process that actually is being offered, but I don't know that it's being widely used at this point, that closes the loop between an electromagnetic brake system, the ABB FC mold system, and their monitoring system so that the magnetic field can be adjusted dynamically to control the stability of the meniscus and stability of the process. Okay. Well, everything I've showed you so far are things that are already available, right? They're out there, and they're available for people to use. I want to talk a little bit now about some of these more interesting and newer technologies, because in the end, I think there's room to move forward quite a bit. And one of the first ones I wanted to mention was the use of this thermal mapping using Rayleigh scattering. These fiber optic systems, as I mentioned, can do very high resolution measurement on the order of 0.5 millimeter. They require no special manufacturing to put sensors within the fiber like a Bragg grading system does. And as a result, we can utilize off-the-shelf telecommunications fiber as a sensing device. So it's not only low cost, but now we can use a single fiber, and with the right numerical aperture, can bend it at tight enough radiuses that we can weave it back and forth in the mold. And under those conditions, create a very high resolution thermal map of a process. So this is an experiment that we've done in our labs that shows a mold where the fiber has been woven back and forth within this mold plate. And then we put it into a system. There we immerse it in molten steel to do a heat transfer measurement and actually extract the shell growth and measure that shell growth. And we've used this largely in our labs to study peristectic behavior. Peristectic shift is a function of chemistry. Just to show you what this looks like, there's our plunging device with the instrumented single fiber, and that's the raw fiber signal. And so if I back up, you can see that that single fiber actually can give us, I'll try it again, one continuous profile of temperature that then can be remapped into a thermal map. And these are some examples of thermal maps. This happens to be a steel, with carbon at various levels in it, but with silicon, which actually extends the peristectic to the higher carbon range because of the nature of the silicon providing essentially ferrite stability. And as a result, we can watch from these thermal profiles the impact of shell pull away on the heat extraction very clearly. And in this case, you can see normally we would have the peristectic running between about 11 and 14 carbon or 16 carbon. And here you can see because of the silicon, it's pushed up to the higher carbon levels. Just to give you an idea of the resolution of these systems, there's a shell profile, and the thickness profile corresponds very well with the thermal mapping profile. And so we're actually able to get very high detailed information in this, this type of sensing environment. So these fibers, when they're good up to about 700 C, and in this environment, we can actually use them in other processes as well. And this is actually an aluminum casting, sorry guys. But given that the fiber has temperature measurement capabilities of about 700 C, this is actually a really good test to show what the single fiber is capable of in a solidification environment. And so we've actually put a fiber across the mold cavity and actually measure the thermal arrest associated with solidification, in this case for a relatively pure aluminum. And you can see, of course, the arrest shows a pretty good uniformity right where it's supposed to be at about 660. And The nice thing is on the lower right, you can actually see the variations in the local solidification time, all extracted with a single fiber. We're also putting these in linings. You know, one of the downsides of using Beryllium scattering or other like Raman scattering systems is you've got very low resolution. But if we can put these Rayleigh fibers in that environment, we can get very high resolution profiles in, you know, refractory lining systems as well. This is some of our laboratory experiments in a mock tundish where we've put a fiber in. And I guess I'll show it poor. So we actually expose it to an environment simulating essentially a dry vibratable tundish lining system. And then we actually take that fiber path through the permanent lining, and we can actually replay the thermal profile going through that permanent lining and passing through the insulating linings. And once again, one fiber giving you a whole profile of information. So we have also now applied this in plant environments and put them in a commercial tundish. And one of the things we've learned here in this tundish environment is that when spray lining systems are used for both insulating and spray linings, that there is a significant delay in the time for which you drive the moisture out of the system. And of course, you can see that thermal profile below and the arrest right around the water, you know, evolution from the lining. And it extends well past the preheat period into, you know, many, many hours into the cast. This is our high risk for hydrogen pickup, for example. And these types of sensors are really good at sensing those kind of events. So I mentioned that we did some measurements in aluminum, but you know, if you're like me, you want to do it in steel, right? So how do we do that? One way we do that is we move to a different fiber. In this case, single crystal sapphire fiber, which can be grown now to, like as I said, about 2 meters in length, about 125 microns in diameter. And that diameter is too wide for it to serve as a single mode fiber. So it's a multi-mode reflector, and so we have to do special things. We have to inbred sensors. And so we use a femtosecond laser to put the lines in to create the Bragg gratings. We also use special mode scrambling technology to highlight the key signals we're most interested in. And with that technology, we've been able to demonstrate ability to measure temperatures well in excess of 1600 C that you would see in most steelmaking environments. In fact, pushing 1850 C. The lower right shows a correspondence of the temperature measured by a Bragg grating with one from a type B type thermocouple, just to show that these things track each other very well. This is actually doing a great job tracking the temperature changes in a system. On the left, you actually see the raw signals that show for 2 Bragg gratings, the peak shift is a function of temperature. That's what we're actually tracking to measure the temperature. So we monitor where these peaks shift to and then correlate that frequency shift directly to temperature. These can also be used for strain if you want to use them in a strain environment. You also notice there's a significant thermal emission that we see in the fiber because we're getting upwards to steelmaking temperatures at 1600 C. There's potentially applications for using that for information as well. So we've actually taken these fibers and put them in commercial alumina carbon and zirconia carbon refractory systems because our interest is actually embedding these directly in the steelmaking process. And so we've demonstrated that we can do measurements quite well with these fiber systems in conventional refractory environments. And actually this shows a sapphire fiber system with 3 Bragg gratings that measure the temperature along the length of immersion of a probe. And the middle one is actually compared to a thermocouple. And you can see, again, the relatively good correspondence of the temperature with the thermocouple position, but we have the added benefit of having multiple measurement points along the length of the fiber. So we can actually measure gradients along that environment. Distributed temperature measurement is an important one, and we've actually also been able to demonstrate now that these fibers can look at a larger number of sensors than 3. In fact, we've now demonstrated up to 10 FPGs in a fiber that is a sapphire fiber system. And then each base frequency will shift as a function of temperature, and each can be tracked to have an individual measurement point along that length of that fiber. Our holy grail is actually to demonstrate these in a commercial refractory. So we've actually had some trial nozzles made that are going to be put into a commercial test here in the next, actually, month or two, where the fiber is embedded into the sidewall of a submerged entry nozzle, and we can actually measure the temperature gradients along the length of the SEN for ultimately things like wave measurement, submergence depth monitoring, and so forth. And I also mentioned the interferometer technology. Interferometry, it turns out, can be quite useful for measuring things like solidification gap development in the casting process. This is an example of two interferometers placed into a static mold. In this case, the demonstration is with aluminum, but what we're able to show is that that sensor has direct line of sight into the mold cavity with a very small, about 125 micron sight hole. And the surface of that solidified steel or aluminum can actually serve as a reflector, and we can actually dynamically measure the gap during that process. So this just shows the interferometer setup and some other things, but here are actually some of the results. And if we combine it with some of the Rayleigh backscattering fiber temperature monitoring, we have all the information we need to monitor the thermal profile through the mold wall, through the solidification cavity, but also directly measure the evolution of the gap, which is a very difficult measurement to do. I know there are some people in the audience here who have done it with LVDTs or Tempesonics. It's very difficult because you have to compensate for those temperature changes along the connecting points. Here, this interference pattern is temperature insensitive, so it's really a pretty benign sensor and gives you a lot of really valuable information. So am I going too deep, guys? No? Okay. So here are some measures. The other thing we're thinking for these interferometers is that they are really potentially have a lot of value for doing measurements in the caster in the future. Not only can we monitor, slab shape and other things directly exiting the mold, but we also potentially can use these for measuring things that Brian would be really interested in, such as inner roll bulging behavior. And these sensors, because of their temperature insensitivity, could be a really good candidate for this. The other thing that we're actually exploring, this is just a high temperature calibration showing the measurement of a calibration block at 1200 C versus room temperature, just showing that we get the same measurements regardless of the environment temperature. It's actually pretty exciting. One of the things that we're looking at right now is, can we put one of these in a mold and actually get information about the flux and the flux crystallization directly? And if we use these interferometers, the reflection off of reflecting surfaces can give us a lot of information. What's the interfacial gap between the surface of the flux layer and the mold? Is there a presence of a crystalline layer, and where is it forming? And potentially even reflections related to the flux contact with the shell surface itself. So we can monitor all three of those with a single interferometer by actually taking the interference patterns and in the frequency domain identify those key peaks that are related to that interferometry pattern. And so we've been able to detect things like flux crystallization. This is a small, essentially, cell experiment that we've done that demonstrated we can see these things. Actually, I think it's showing there. Okay. So everything we've talked about so far has been either position or strain. How are we doing for time? We're good? Okay. And I also wanted to mention that these fibers can measure strain. This is just a demo that our guys like to show that basically shows how a fiber attached to a surface can be used to directly measure dynamic strain in real time. And it's actually pretty impressive that this can be done. We've also taken fiber optic sensors and we've applied them in the real world, and we've put them on continuous casting support beam structures to do essentially roll force measurements to detect the presence and absence of liquid core position. And the beauty of using fiber optics over conventional sensors in this environment is that these sensors can be multiplexed. They can be daisy-chained. And so we can have one fiber feeding a large number of sensors and instrument a whole segment or a bank of segments with one fiber, as opposed to having power run to doing strain gauge measurements at each location. And so it's pretty trivial to put on. In fact, these particular sensors were glued on the surface after cleaning with acrylate cement. And they actually produced very nice signals. In fact, we've been able to demonstrate this on a continuous caster, and have actually been able to use their internal digital twin model of the liquid core position and compare the strain measurements and actually show exceptional correspondence. In a couple of cases, we actually see operating conditions that cause a deviation from their model prediction, largely because of changes in mold heat removal that aren't accounted for in the model. And so these are going to be great tools if you're running a continuous caster and you need to know where your liquid core is, either for productivity or if you're doing soft reduction to improve center line. These are really great tools that can be used, and they're relatively easy to install. The other thing about these fibers is that they're pretty sensitive. We can see what looks like noise in some of these fibers. And you'll notice we have two signals. We, in this case, used FPGs mounted longitudinally and transverse, such that when the roll force imparts deflection to the beam, we see a positive increase in the longitudinal direction, but a negative due to Poisson's ratio of the beam. And so it's really easy to separate temperature and strain doing that. But the signal and noise on that individual signal can also be separated out. And in the frequency domain, we've been able to show that you can actually see bulging and bent roll conditions in the machine using these sensor technology. So, last area I want to talk about is the potential for using fiber optics as a remote sensor for doing slag and flux chemistry measurement. And here we've built a demonstration system that uses essentially a fiber optic carrier to a Raman probe system that can actually tolerate reasonably high temperatures. And we can actually do real-time measurements of the Raman spectra on fluxes and slags at high temperatures. And in fact, we've demonstrated 14 to 1500 C so far. Our first study on this was actually to look at mold fluxes and determine whether we can develop a probe that might be able to detect the shift in composition for some of the exotic steel grades we're trying to make, such as Generation 3 advanced high-strength steels, which have exchange reactions that cause actually pretty tremendous shifts in the composition of the flux. So this is actually what that probe looks like, and one of the small test conditions that we use in the lab to at least extract the Raman spectra and begin to understand it. And what we've been able to show is that we can not only collect that Raman spectra, but we can look at key regions of that spectra and correlate it directly to the slag structures. Turns out for silicate slag systems and flux systems, the so-called Q region, which represents the polymerization state of silicate chains in the slag, can actually be detected by their Raman signature. Each one has a unique frequency. And we can take the Raman spectra and deconvolute that spectra in order to extract the fundamental components. Those fundamental components can actually be used to not only calculate the composition of the flux, but they can also do things like estimate viscosity of the flux, because it's the polymeric state of the slag systems that actually correlate to the flux viscosity. And so we've been able to correlate a lot of these things, and this is work that we've done on the spectra deconvolution in the in the flux systems. And we've also are now correlating those compositions and basicities of these fluxes to the structure based on the ratios of the Raman spectra peaks that are deconvoluted. We're also doing this not only for flux systems, but we're developing the same technology now for monitoring electric furnace slags, which is very exciting because the ability to do real-time slag analysis would be a real boon to the EAF industry. So I'm reaching about the end here, and we'll have some time for questions. So just in summary, new and existing sensor systems based on fiber optics really show great promise for applications in the extreme environments of steel. These highly distributed and remote sensing capabilities promise to provide both researchers and operators with a view into their processes that was previously unattainable. In fact, one of our past recipients was Keith Brimacombe, and Keith always had a dream of having the intelligent or smart mold. And this is now becoming a reality. I think these sensor systems are providing us with all sorts of new measurements that can be used to move forward with Industry 4.0. Sorry, lost my thought train there. So these systems really support the movement into Industry 4.0. So right now I have little doubt that this combination will provide significant benefits to the industry, and the industry will see these benefits as measured by productivity improvements, cost reductions, quality improvements, environmental impact, and overall efficiency. And just in closing, I think that Henry Marion Howe would be really impressed with how far the science has come and the technology of steelmaking has advanced, and would also be impressed with the promising advancements that are yet to come. And so with that, I'd like to say thank you, acknowledge some of my core team. This was a large effort by a large number of people, including funding through the government agencies and the Defense Logistic Agency and our own Steel Center. And so I just want to say thank you for all of you who have supported this work. And we have the government disclaimer at the end. Thank you.
So we have time for a few questions. If anyone would like to raise their hand, we'll pass around the microphone to you. Yeah, no, there's one right.
Yeah, I saw one over here. Okay, you've got one here too. Oh, go ahead.
Good morning, Professor. I'm Daniela from Brazil, and I'd like to know if this technique can be used in the spray chamber in the continuous casting.
In the spray chamber?
Yes.
Yeah, we believe so. One of the challenges, depending on the type of measurement, one of the things we're looking at right now is an optical rotary joint that would allow us to instrument rolls, for example. And so that could be a really exciting development for spray chamber measurements, because we're all making guesses about the heat removal by roll versus spray contact, for example. Bulging measurement is another area. I think we have to ensure that we can see through the steam environments or keep it clear, but that appears to be doable.
All right, next one.
Thank you for
Okay, thank you.
lecture. Oh, sorry.
Oh, thank you. Go ahead.
So one question.
Yes.
When we measure by thermocouple, we know temperature, we measure temperature, but we know distance.
Yes,
So one variable. In your case, we have several variables.
absolutely.
How you calibrate?
How do you calibrate? So the initial fiber, if we're talking specifically about Rayleigh, in a fiber Bragg grading system, that reflect-in frequency shift is well defined and can be calibrated offline. In an installation where we're putting a Rayleigh fiber in, typically what we do is we'll run a calibration under a known thermal condition by capturing the spectral range along the length of the fiber, and then use that as the basis for the further shifts. So the one Achilles heel is that you have to have some point where you measure at a known condition and then shift from that.
Thank you.
Okay, another question? Yep. Charlie has one. Go ahead.
Sorry, the lights are bright.
Oh, hi.
Oh,
Ron.
there we go.
Excellent presentation. I really enjoyed it, and I think I learned a lot. My question is in particular the fiber optics in the machine where you're measuring strain. Can you speak to the resiliency of those fiber optics, and speak when you mentioned daisy chain together? If they don't last the life of if they can last as long as the life of the segments, are they modular enough to like you can take apart, put back in, and have no compromise in it?
Yeah, those are all really good questions. And I have to say we haven't tested over the surface life of a segment, but our indications are, particularly for those measurements, that we can put a cover over those sensors and isolate them from operators standing on them and potentially breaking fibers, which is usually the biggest risk, right?
Okay,
But the other thing is that these things are stable for a long time, and these fibers can be spliced in the field too. And so we can always jump out and jump in a new sensor where needed and still maintain the daisy chain of measurement. Well, this side. Hello.
Hi, thank you very much for this presentation.
Thank you.
Especially regarding the slag analysis. Did you also look into OES technology to establish?
We haven't looked at that one yet. We've right now are focusing on developing the Raman technology just because it seemed most suitable for our first program, which was related to measurements in mold fluxes. But other methods are certainly viable with fiber optics. In fact, you know as well as I, fiber optics are often used to bring signals back to the main unit from a remote testing station. And the extension of that is taking it all the way to the process. And so I think it has value to investigate. It's just not been on our radar at this point.
Thank you very much.
All right, I have a question over here.
Yes.
Thank you, Professor. This was very interesting. I would have a question for the slide where you displayed the temperature distributions for the different carbon steel grades.
Yes.
Low carbon, peritectic, and
Yes.
yeah.
Do you want me to pop that one back up?
Yeah.
I can do that, I think.
I think it would be interesting.
Let me see if I can find it here real quick. We're close. There it is. So this is the one you're talking about right here, right? Yes.
Yes, correct. Because the impression I got out of it is that the thing that is special for peritectic steel grades, it looks like it's not so uniform. Yeah.
Right.
So you have
right. Well, there are two things in the peritectic. One is non-uniformity and pull away, right?
Yes.
And we can see the effect on heat extraction here. Right now, we're not seeing a lot of the details, and it's probably because of the size of our test that you're not seeing all the shrinkage details.
But is the conclusion that the non-uniformities in the formation of bulging shell peritectic shell grades is because of a non-uniformity in heat flow?
No, I think it's directly related to the nature of the peritectic solidification. In fact, most people would say that it's the density change and the abrupt density change from, delta ferrite to austenite that induces strains that actually cannot be withstood by the shell and create that buckling.
Thank you very much.
You're welcome.
Another question?
Yes, go ahead.
I have one.
Over the
Okay.
side.
Yeah. Thank you, Professor Ron. A fantastic presentation. This is Somnath here. I was most fascinated by the last part when you talked about the slag characteristics. I've just a small question. When you take the optic fiber probe very close to the melt surface, do you need any particular filtering or shielding? And if you use any filtering against this, let's say the radiation, does it interfere with the fidelity of the signal that you carry?
So one of the things we do in that environment is, first of all, we harden the probe so that it can withstand reasonable temperatures. We're never going to have a probe that directly survives steelmaking temperatures. But if we can get close proximity, use an immersion tip to isolate the environment, then we can actually avoid some of the incoming reflections from the surrounding environment. And one of the things we do in these tests is that we will take a background signal and then extract the background signal from the Raman spectra. And that actually helps us identify the key peaks. Does that make sense?
Any additional questions? You can ask.
Yes, Rod.
Very, very good talk. Terrific.
Thank you.
question. You said of Heraeus electronite.
Right.
They've got this silica.
Yeah, it's a fiber optic.
It pushes in.
Yeah, so it's a jacketed fiber that it gets injected into the steel directly.
Yeah. And then
And
melts.
from that, they extract essentially a pyrometric signal, right? So it's thermal emission transmitted back to a remote sensing device. Now, the configuration and the immersion actually create a cavity that behaves close to a black body condition. And so that actually takes away a lot of the ambiguities. If you were using a pyrometer up above, you would have to correct for all the emissivities in the surrounding environment, right?
But how long does it last there?
Oh, it's actually consumed pretty quickly, and it's
Yeah.
continuously fed, actually.
Yeah.
So they can also then, of course, measure positions with movement and actually get position data from that as well. And in fact, I think they're in the audience here. They can probably talk to you more about it.
Or you can visit them at their booth.
At their booth.
Down
There
in
you
the
go.
exhibit hall. All right, we have time for just one. Okay, go ahead. Anna, right there.
Thank you. Excellent presentation. I'm Buddy Lee with Mesa Associates.
Thank you.
I am very interested in this technology as an input to a bigger picture item, which is artificial intelligence.
Yes.
Can these top sensors be used to predict the remaining useful life of any of the refractory, the rolls, any of the components that you've discussed today? Would you mind just addressing
Well,
that for a second?
and in fact, we're actually looking at these sensors in a variety of applications for that purpose. When you talk about refractory linings, we're applying these not only around EAF burner systems to predict potential damage and water leaks in that environment, but also to look at the refractory wear over time. So I think these can very easily do that. We're also putting them on spray-cooled panels on EAFs so that we can detect local hotspots in that environment. And we're still in the early stages, but we're doing some pilot installations, it turns out, at 2 plants in the US, one at Big River and the other is CMC Birmingham. And there are 2 different type of panel designs that we're trying to sense with these fibers. You're welcome. All right.
Any additional questions? One last one right here.
I like the last question. I just want to add to that a
Yes.
little bit. The connection between your sensors and when you talked about that digital twin, and
Yes.
how do you see that playing out in the
Well, in the end, all models require verification, right? And, the casting digital twin that I talked to you about, there are always assumptions made, right? And, one of the things that where we see deviations from the actual model predictions is under transient events that are not readily predicted very well in these processes. I'll give you an example. We saw extension of the liquid core as a result of doing a submerged entry nozzle change that disturbs the lubricating environment of the mold and then actually affects the solidification length enough that you can actually see it. In those conditions, we see deviations. Under steady state conditions, the models are pretty well tuned, and people have already done other measurement methods to fit them. So, I think, for me, it's all about having a tool to verify and refine the models. And, I've worked with Brian over many years, and we have worked together collaboratively to do this in a lot of areas. And I think it's paid off in general, right?
Okay, maybe time for one last question. I shouldn't stand for. Anyone? Last chance.
Okay, you've got one.
One
over
last
there.
one, Dr. Spear.
Uh-oh, the product question.
No, totally different, but thanks for your talk, Ron.
Oh, thanks.
So I know at your institution you also have a sort of ceramics and glass program.
Yes.
Is there any work going on the glass for the sensors? Is that viewed as an
know,
opportunity in the glass
This is
community?
something, yeah, you're absolutely right. This is an area that we really need to develop because one of the things about fiber optics is if you're doing, transmission for telecommunications, you don't want Rayleigh scattering, right? You want it to be as low as possible, right? And we actually prefer fibers that are noisy, right? Because they give us a higher signal noise ratio. And so one of the things that I would ultimately like to spend time on is how do we create improved dopant environments that allow these Rayleigh fibers to go to even higher temperatures. Because today, you get above 700, and the dopants that are used in those fibers start to migrate. You know, even in these systems, I haven't mentioned it, but we typically do a stabilizing anneal before we use the fiber, just to stabilize the dopant locations. And that lets us run stably at about 700. You go above that, you start to see drift. And it's more a function of the index of refraction change than anything. So, that answer your question? Yeah, thanks.
All right, Ron, on behalf of the Awards and Recognition Program Committee and all of the AIST membership, I think you've given a wonderfully fitting tribute to Henry Marion Howe in how far this industry has taken the art of steelmaking and made it a science of steelmaking. So on behalf of all of that legacy, we want to thank you very much as our 100th Howe Memorial Lecture Award recipient. Thank you.
Thank you, Ron. You want to do it this way? Thank you. I'll let you take that back, right?
Congratulations.
Hey, thanks.
Well
Went
done.
all right?
Ah.